What we did in the previous class is that we actually defined two different processes of transition. So one of the process we called absorption, where a photon comes, and if the atom is in a lower energy state, the photon actually excites this atom and it actually jumps to the upper level or the higher excited state by absorbing the photon. So this process was termed as absorption. The second one was the atom itself was in a higher excited state, and then h bar omega energy photon falls into this atom, and then this actually causes something which is known as stimulated emission. That means because of this perturbation, the atom in the higher excited state actually jumps from the higher excited state to the lower excited state and reaches the state A, which has lesser energy, with the release of another photon. I have written two photons. One was the initial photon, which actually affected the perturbation and which caused the atom to transit from higher level to the lower level, and the other one is the emission of photon because of this process. So this process is termed as stimulated emission. Now we actually can conclude that what are the rate of these two different processes, and we said that we will be actually complicating our lives by introducing some temperature. So we have this system where we had several atoms on the walls of the container. You can think of it as a continuum, and then inside the container there is some radiation field. Therefore this electromagnetic field is interacting with the atoms on the walls of the container, and thereby actually starting these two different processes. One is known as the absorption, another is known as the spontaneous emission, stimulated emission. Spontaneous emission I will come later. Stimulated emission. And since the system is in equilibrium, we said that the transition rate from upper state to lower state due to this stimulated emission is basically proportional to the number of atoms, which I denote by NB, which is there in the state B, and on the number of photons that is there within the cavity within the frequency range omega in the radiation field. So this number of photon, as I had explained in the last class, is basically proportional to the photon energy density, which I have denoted by U omega. So therefore the transition rate should be proportional to NB, should be proportional to the number of photons, which in turn is basically proportional to the photon energy density. And you can think of this coefficient BA to be a proportionality constant, and this constant is termed as Einstein, or known as Einstein's B coefficient. Similarly, for the absorption also, the state A actually is excited to state B by absorbing a photon of energy h bar omega. And therefore you can say that the rate of transition from A to B is proportional to the number of atoms in the level A times the number of photons, which is given by U omega, and then which is of course being multiplied by a proportionality constant, which is a different proportionality constant than this BBA. Later on we will show that this and these are basically the same, but for the time being I am denoting this BBA and BAB to be two different constants. Now this part I am skipping because I had explained this laser to some extent in the previous lecture. So I will straight away come to the discussion here, where I have said that the rate of absorption is basically proportional to the number of atoms available in the ground state. That's what I have argued just now. That means this ground state atom is capable of absorbing a photon, and it will also depend on the number of photons available, which is in turn proportional to omega u omega. And finally, definitely there should be some B coefficient, which I call the transition coefficient, which is also known as Einstein's B coefficient. And if we consider all these things, I am stressing this physical meanings of these objects, this BBA and the rate, simply because I have said that the radiation is with equilibrium at some temperature, finite temperature T. Now, what does that mean? That means that if you look at the rate of change of NB, that rate of change of NB, it should be 0. As I have said that the question was, I have said that this can we achieve equilibrium? We can only achieve equilibrium if the rate of change of the number of atoms in the B state is 0. So that means, how can I tell what is NB dot? The NB dot, that means the rate of absorption minus the rate of stimulated emission will be basically the rate of change of atom number in the state B. So I know what is the rate of absorption. I also know what is the rate of stimulated emission. And if I simply do this calculation, the final answer that we will get is this one. Remember, we had actually used this statistical mechanical result that NB by NA should be basically given by this Boltzmann distribution e to the minus beta h bar omega. And this equation is kind of a peculiar equation, simply because you know that this quantity is non-zero, you know that this quantity is non-zero, therefore this object within the bracket should be equal to 0. So that means our condition for equilibrium is asking for something which is extremely peculiar. Why am I saying that this equation equal to 0 is a peculiar equation? I am saying this simply because the B coefficient, which I have introduced in order to define the rate of transition, this B coefficient, it seems from this equation, is that this B coefficient depends on the electronic structure in the atom. That is what it should depend. But from this equation, I can see that it is dependent on temperature too, but it should not depend on temperature in principle. It should only depend on the structure of the atom or the electronic structure of the atom, which will kind of tell you what kind of transitions are possible and why they are possible. Therefore, this B coefficient, which determines the rate of spontaneous, the stimulated emission as well as the absorption, is a sole property of the electronic structure of the atom and not the temperature. Therefore, this cancellation is not possible for any arbitrary temperature. And we also note this important fact that the photon energy density, it is not appearing in this equilibrium condition at all, because I know that this object cannot be 0, I know that this is not 0. Therefore, this condition for equilibrium, nowhere it actually takes care of the fact that there is this photon energy density. That means, if there is no photon energy density in the equilibrium condition, that means that the equilibrium has not reached, it is not possible. But I said, if you remember the very beginning of yesterday's class, I said that there is equilibrium in the system. That means we must be missing something. Some factor is missing in this simple definition of the rate of change of the number of particles in state B. So what is that? In fact, it turned out that there is another process which we have not considered at all, and that another process is termed as spontaneous emission. What does that mean? It means that it is an emission rate that does not depend on the thermal photons. That means whatever be the rate of spontaneous emission, that should not depend on the photon energy density, or in turn that should not depend on the photon number. It only will depend on the number of atoms which are available in the excited state, in this case the state B. Remember, we actually had written for stimulated emission, this object we had written that rate of transition rate is basically proportional to the number of photons, proportional to the number of atoms in the higher excited state times this coefficient. Now it has to be modified. It has to be modified to this equation where I am saying that apart from this stimulated emission process, there is something else which actually is proportional to the number of atoms in the B level only. It does not depend on the photon number. And that process we call the spontaneous emission. That means if you look at this spontaneous emission process, it is a process where an atom actually jumps from higher excited state to lower excited state with a release of the photon. Still, it is not being at all perturbed by any other photon. It just jumps from the higher excited state to the lower excited state. Therefore, its rate should only be proportional to the number of atoms which are there in this B state. And of course, after this jump, it will actually be accompanied by this photon also. So this process is termed as spontaneous emission, where there is a downward transition with the emission of a photon. But as I am stressing many times, that this is without any applied electromagnetic field. So now let us actually consider the equilibrium condition once again. Earlier I wrote this was NB dot has to be 0, that is the equilibrium criteria. Now I am saying that it should be defined as rate of absorption minus rate of emission. I am not saying what kind of emission, it just says that there are spontaneous as well as stimulated emission. So we have to take into account both contributions when I write down the rate of emission. So I write everything down using the proper definition of the rates. This was the rate of absorption, this was the rate of stimulated emission, and this was the rate for spontaneous emission. And here I had defined a new coefficient ABA, which I call Einstein's A coefficient. It is called Einstein's A coefficient. I have used this subscript BA. You will see in many books there is no subscript. Many books actually simply write it as A times NB. Both symbols are actually equally applicable. Here this BA or here this BAB, whatever, I mean ABA or BAB, whatever subscripts I have written, they really does not mean anything. It just tells you that from which state to which state the jump or transition is happening. Anyway, so from here you can actually write down this ABA, the Einstein's A coefficient, in this form. And therefore your U omega BA, the energy density of photon, can be written in this format. I have been able to write this as e to the plus beta h bar omega BA, because Na by Nb by definition, if you go back and you look at the three criteria, the second criteria of them was this equation. Now of course I have also written from Planck's distribution what is U omega BA. In fact, it should be U omega BA d omega. There should be a d omega. Anyway, it does not matter at the moment. So this tells you what is the photon energy density. So if you now compare this equation with this equation, because both of them, the left hand side is this, then clearly you understand one thing, that because this factor is 1, then BBA by BAB has to be equal to 1. That means BBA should be equal to BAB. That is one criteria that you can get from this. And similarly, you look at this coefficient ABA by BAB, and it is immediately clear that ABA by BAB should be nothing but h bar omega cube BA divided by pi square C cube. So we have figured out the relation between the Einstein's A and B coefficients, and also, as I have claimed at the beginning of the class, that there is a relation between BAB and BBA. In fact, they are same. That also has been proved using this relation. Now, there are several points here that I want to mention. First of them is the fact that spontaneous emission does not care about the photon energy density. That is, whatever may be the number of photons flying around, irrespective of that, there can be an emission process which is not being triggered by these photons. So at first sight, it might be very difficult to visualize this thing, because it is something which we are not very much familiar with in our so far as the quantum theories we have discussed, or the daily life we see around ourselves. Nothing of this kind of this sort of thing happens around us, that someone was sitting on somewhere and immediately, without having any perturbation to the system, that actually jumps to another state. That we do not really see. So it is basically far from clear why spontaneous emission should at all occur. Okay, so it was not very clear, because if the atom is in a stationary state, of course you might say that okay, it is in some excited state, but still it is in a stationary state, and there is no reason that if I do not apply any perturbation, the atom should actually jump to a lower energy level. Here what happens in case of spontaneous emission is that without any applied radiation or electromagnetic field, I can see that the atom jumps from higher to lower level with the release of a photon. So obviously something deeper is happening, and that something deeper is actually beyond the scope of this course. What is happening here is that at a deeper level, you can actually think of spontaneous emission as some kind of stimulated emission due to vacuum fluctuation of the electromagnetic field. Now, I have said a few complicated statements. All these things are basically related to the quantum nature of electromagnetic field that unfortunately is not a part of this course. So in fact, there are something called vacuum fluctuations in quantum field theory, and because of those vacuum fluctuations, one can say a process like spontaneous emission can occur. But anyway, as I said, this is beyond the scope of the discussion of this course at this level. So now if we actually take a look at this relation, let us look at this relation once again. You can see that I have written this as ABA by BAB into U omega BA. This should be equal to this object, exponential h bar omega BA by KT minus 1. But this also tells you something, that there is this spontaneous emission coefficient and there is this stimulated emission coefficient. It better be BBA anyway, because we have seen that ABAB is equal to BBA. It does not matter. But what this tells us is that the rate has different effects on different temperatures, or at different temperatures, because you can see that you can look at this expression and you can clearly see that the increase of T actually increases the number of photons per unit volume, and therefore at higher temperature the stimulated emission process occurs, which is clear from this graph. You can actually look at this thing, and this is the region where you have higher temperature, where stimulated emission occurs. However, at lower temperature, the black body radiation as you know, has little number of photons. So most of the transitions that occur are basically happening due to the spontaneous emission process, which is happening in this region. So I mean, you can figure out where this function actually becomes 1. From there you can figure out this, what should be the value of kt, and then that roughly divides the two regions. Okay, so now let us actually come to the interesting part of our discussion once again. Let us actually go back and discuss this atom light interaction. As I already stressed the fact that light here means electromagnetic wave. It can be visible light, it can be infrared, it can be ultraviolet, it can be even X-ray, gamma ray, whatever, any electromagnetic wave, I will call them collectively as light. Now, there are few assumptions that are going on in here. The first of the assumptions is the fact that let us first focus on the electric field only. Although we are talking about electromagnetic waves, there is a E part and there is a B part, but the effect of magnetic field is basically very weak, and it is weaker by a factor of V by C, where C is the speed of light, which is nothing but proportional to the fine structure constant alpha. So B field is always weaker in this scenario. And second important point here is that we are thinking of optical frequency, which is basically 4000 to 8000 angstrom, the visible frequency. And this lambda therefore is greater than the size of the atom. A0 is, remember, A0 was the Bohr radius. So if I am dealing with the electromagnetic wave whose wavelength is of the order of 4000 to 8000 angstrom, which is much higher than the size of an atom, which is just 0.5 angstrom, we can simply neglect the spatial variation or the dependence of the electromagnetic field or the electric field in our case, because we said magnetic field's effect is anyway weaker by fine structure constant. So we can neglect the spatial variation in the electric field because of the fact that lambda is much greater than the size of the atom. So whatever variation occurs, since my atom is extremely tiny compared to the wavelength of the photon, we really do not care if there is any spatial dependence or spatial variation of the electric field. Now let us actually choose the form of the electric field. We choose the electric field in any arbitrary direction, where n cap denotes the unit vector in the direction of the field. So this is my atom, this is the electric field, and this is the unit vector, and these are my x, y, and z axis. And of course, as I have stressed here that we should neglect the spatial variation of the electric field, this E is only dependent on time. There is no x dependence, as we have just explained. Now let us actually choose the electric field to be of this form, 2 E naught cosine omega t n cap. Therefore you can immediately figure out the scalar potential. The scalar potential in this case is phi should be equal to minus r dot E. E is a function of t, remember. And this is true because gradient of phi, if you calculate it, is minus of E. However, you must remember this, that it is not true in the presence of the magnetic field, whatever we have done here, but we are actually ignoring the magnetic field anyway, so it does not affect our calculation. So what should be my time dependent Hamiltonian? Of course, this should be q times the phi, the potential, so which is nothing but minus q times r dot E. Now this E is a function of time, so perturbing, this is basically my perturbing Hamiltonian due to the coupling between the electric field as well as the charged particle. And remember that this object q r dot n hat times Et is my h prime of t, but this reminds us of something, Aren't we familiar with this quantity q times r vector? This is of course your known dipole moment operator. So because this is operator, this r vector is there, but this is a quantum mechanical quantity, therefore I will call this as a dipole operator. We define the dipole operator d as q times r vector. So this is an operator simply because r is an operator in our quantum mechanical language. That is why d is also an operator. Now, if you look at this expression of h prime of t, I can write this as minus d dot n hat times et, and then we substitute this e of t as 2 e naught cosine omega t. Then this is going to give me 2 times minus d dot n hat times e naught into cosine omega t. But now you remember, this is exactly same as our harmonic perturbation Hamiltonian, the h prime part. So remember what was my h prime of t for harmonic perturbation? For harmonic perturbation, my h prime of t was 2 times h prime cosine omega t. This h prime is time independent, and let us not confuse ourselves. So let us denote by this h prime. So the h prime that we are talking about here is some thick h prime, which is nothing related to, which has nothing to do with the time independence of the Hamiltonian, time dependence of the Hamiltonian. This h prime is completely time independent, and it has this form for this particular problem. So h prime in this case is basically time independent one. It's a dipole interaction for our particular problem. Now you recall our transition formula, the probability of transition from B to A, which we derived using Fermi's golden rule, or this is basically the Fermi's golden rule. So this is 4 h prime AB mod square, and then divided by h bar square, and then this is nothing but sine square omega BA divided by omega BA minus omega by 2 into t divided by omega BA minus omega. So this is what we are familiar with. We just simply replace this h prime AB with this object. So I will have 4 e naught square. This was h prime AB, this h prime AB. So yeah, that is what the confusion is. So we have 4 e naught square d dot n AB mod square by h bar square and sine square, this usual stuff. Now I have some more observation to make. Look at this expression of PAB, which has this e square sitting here, or e0 square rather sitting here. So what I am going to do now is that I am going to relate this e naught square with the energy density of the electromagnetic field. So I know that this UE, the electromagnetic field energy density, is written by epsilon naught by 2 electric field square plus 1 by 2 mu naught the magnetic field square. In fact, if you have forgotten this thing, you should go back to 102. We have discussed in the class of 102 what is the energy density in the electromagnetic field. Now what we have also shown in the class of 102, also, I mean, I'm sure that it has been discussed in your usual electromagnetism course also in the previous semester. So the electric and magnetic contributions are basically equal, therefore UE can be written as epsilon naught into E square. And then E I know that is 2 E naught cosine omega t, so we make the square of this thing, therefore this is your UE. But then then I have to actually average over this quantity full circle. If I do the average over the full circle, then this quantity becomes 4 E naught square epsilon naught times half, simply because cosine square omega t integrated or averaged over over a full cycle is just half. So this object is 2 epsilon naught square E0, or epsilon E0 square epsilon naught. So you can see that I can write this object E0 square in terms of the energy density of the electromagnetic field in this way. So what I do here is that I actually replace this object with the energy density of the electromagnetic field and finally arrive at this expression. But you also note that this is true for a monochromatic wave. That means a wave which has a single frequency, and this is true for a single frequency omega. But in many applications, the system is exposed to many different frequencies. Your radiation may contain a range of frequencies of electromagnetic waves. So in this case, what is the prescription? If you remember, the prescription is you replace this u of e as u omega d omega, which is nothing but the energy density in the frequency range d omega. So that means we started with the electromagnetic field energy density, but now I am saying is that whatever I have written so far is true only for a single frequency. Waves with single frequency will follow this. But when I generally discuss the radiation inside a cavity, that radiation can contain very many different frequencies. So in order to take care of this non-monochromaticity of the incident wave or the radiation field, your UE has to be changed with the energy density in the frequency range d omega. That means whatever equation you have written here, you will write it here in the same form, but now this time you replace this UE average with integral 0 to infinity u omega d omega, with of course this sine square factor sitting here. But again, isn't this actually familiar to us? You go back to our discussion, at least the previous discussion and the last classes discussion. You can actually apply the same argument that we had given there. You see that this object, this function, is sharply peaked about this frequency omega BA, and I had argued for a long time that the main contribution for this integral should actually come from this main lobe, which is centered around omega equal to omega BA. So it assumes when I write the transition probability from B to A, while writing this expression, we assumed that the perturbation at different frequencies are basically independent of each other. So that the total transition probability is basically a sum of individual probabilities. That is why you are allowed to write this. Now, if the different components are basically related by phase, or in other words, this is called a coherent thing, then we should actually add the amplitudes and we should not be adding the probabilities. And there will be, if such a situation arises, then if you want to work with that, immediately you will see that there will be cross terms. That is why for application purposes we will always assume the perturbations to be incoherent. So everywhere when we are dealing with perturbations of or the interaction of light with matter, we always deal with scenarios where the perturbations are incoherent. So with this expression and with the statement that the maximum contributions comes from the topmost the centralmost peak, where the peak is around omega BA equal to omega, and that means That means this quantity is a constant, there is no variation, so we can take this u omega ba out, and only integration that remains is basically this. Now you can actually follow the standard procedure and you can figure out what is the result of this integration. And the final answer that I want to stress here is this one. If you actually transit from B to A because of some perturbation or some other reason, the transition probability is basically given by pi by epsilon naught h bar square u, which is a function of omega ba, times this dipole operator dot the direction in which the dipole operator or the radial distance is, or the electric field is. So this object's mod square times t, and therefore from here you can see that the rate, which is dp dt, is just this expression without this t. So r, or the rate, is independent of time. Now so far we have two vectors in our discussion which depends on the geometry of the atom. This d is the dependent on the geometry of the atom, and n hat is basically related to the direction of the electric field rather. But light comes with all possible polarizations, and this amounts to averaging over all possible directions of n, because n can be any direction, it's a general vector, unit vector. So when I have this quantity in the expression, or this quantity in here, in order to take care of this all possible polarizations, it is always suggestive to take the average of this. So you take the average. What you do here is that you write this equation down in component form, and thereby there will be a summation over I. But now you see that this object, which I called the dipole operator, which is a vector operator, this object can also be complex. So you can have dabi ni star times sum over j dabj nj, and then this dabi star and dabj should always be there, because these d's are just some numbers, so they are not they do not have anything to do with the averaging over the direction. So all the averages should actually be over ni nj. But here also you note these things, these are unit vectors, and you expect that from all these three directions the contributions will be the same. Therefore whenever you calculate nx, ny, and z averages, you will expect that this should be equal to 1, and therefore ni and j average should be 1/3 times the Kronecker delta. And therefore you just put everything back into this expression, and you see what we get is 1/3 dab mod squared. This is the dipole operator. Therefore your rate, the transition rate per atom for stimulated emission from B to A under the influence of incoherent unpolarized light, which is incident from all directions with all polarizations, is given by this expression. But now let us actually go back and let us actually look at this expression of where did we figured out? Here. So we figured out this relation. This we are now going to utilize with this fact and figure out what are the expressions of Einstein's A and B coefficients. So let us calculate that and then we will stop. So ABA by BAB is this, and BAB is equal to BBA. These two relations are already there. And you also remember the Einstein's argument for writing the rate of transition or the rate of probability of transition from state A to state B is written as this. But now if you look at the rate per atom for spontaneous emission, then this is this part that will give you rate per atom, and hence you can immediately write this BBA should be equal to BAB. That is what we have already proved. But now you just compare and you can see that this has to be pi by 3 epsilon naught h bar square DAB mod square. This is what your this expression tells you. If you compare this rate, here I have written RA to B2A, here I have written WBA, but these two are basically the same. Therefore, if you compare this with this means only this part, per atom part, this with this, then you can see that this should no longer be there, and your BAB, the expression for Einstein's B coefficient, should be written in terms of this dipole operator in this following way. Similarly, if you calculate Einstein's A coefficient, again you should use this formula, as well as now you have this expression of BAB. Therefore, you can just utilize this expression and figure out what is your ABA. And this is this form where both these Einstein's A and B coefficient, they are actually proportional to the dipole operator's mod square. So I think it is a good place to stop, because next day I am going to discuss the selection rules, the lifetime of the states, different states of the atom. So let me stop here.